sea level has already risen 20 centimeters due to the global warming.
Hello, good afternoon, and for some people, good evening. Welcome to the seminar to introduce the SIDS Inundation Hazard Prediction Tool. So my name is Akira Mukaida of Remote Sensing Technology Center of Japan, which we call RESTEC. We are contracting, we have a contract from Ministry of Environment Japan, and we work as a chain of Tokyo University, the University of Tokyo, Kanazawa University, Tokyo University of Marine Science and Technology, Nikken Sekkei Shido, and the IDEA Corporation, and us. So this workshop seminar is to introduce the series of tools that we have developed under the contract of Ministry of Environment, Japan. So today, about 1 hour and a half, we have scheduled to introduce these tools and development. First of all, I would like to pass to our Executive Director, Kazuo Tachi, for opening remarks. Tachi-san, please, floor is yours.
Thank you for introduction, Mukaida-san. Good afternoon and good evening, everybody. My name is Kazuo Tachi. I'm an Executive Managing Director of RESTEC. It is my great pleasure to invite you all to this web seminar on seas inundation hazard prediction tool. Under the contract of Ministry of the Environment in Japan, RESTEC with our partners has been developing methodology to protect the coastal inundation in Pacific small island developing states seas since 2016. As you know, the coastal inundation is expected to become more severe due to the sea level rise and the occurrence of powerful tropical cyclones or typhoon, both supposed to be caused by climate change. Our developed methodology can quickly and inexpensively predict future coastal inundation hazard by utilizing satellite data. Last year, we developed a methodology to study the risks to airport operation from possible flooding hazards at the airport in Samoa and the federal state of Micronesia. In this seminar, we will show you our updated effort. First, 22 islands selected from 14 seas, the high wave hazard condition for critical socioeconomic infrastructure are predicted and visualized through the inundation calculations. The result will be made available through the publicly accessible hazard viewer. Second, we developed the basic design of a tool that calculates amounts of the damage to socio-economic infrastructure and loss of the economic ecosystem service, and compare it to the cost of a countermeasure against them. The tool will enable the comparison of the costs and benefits of conventional disaster prevention measures, here called gray measures, and ecological engineering mitigation measures, here called green measures. This will allow us to consider the optimal combination of gray and green measures as climate change adaptation measures. I think this seminar will be very informative for all of participants. We hope that all participants will enjoy the seminar, and we welcome your comments, opinions, and suggestions on how to proceed our project. We will continue to improve our methodology in cooperation with you. Thank you for your attention.
Thank you very much, Tachi-san. I would like to inform you two things. First, I would like you to change your name on the Zoom to identify your organization or institute and the name. Please rename on the Zoom interface. And when you leave this seminar or Zoom, the questionnaire will require for us to help us to understand the requirement or some comment from you. Please cooperate us to understand what your requirement and request. Thank you very much. So these tools are requests from us. Thank you for your cooperation. And first, from us, Restec, introduction to the hazard viewer and also satellite remote, introducing the satellite remote sensing technology. Okay. I will briefly talk about the topics. Okay, so our Restec have the history of to commit on the utilization of satellite imagery, to utilize the satellite imagery. To tackle with the request from the Ministry of Environment Japan, we have to understand the situation in the tropical remote island. The cyclone-induced high wave and storm surge is one of the big issues. In the previous survey, it was identified the hazard maps for the high wave and storm surge have not been developed, and that there is a high need for them in the island countries. So this is a schematic diagram of the how they affect the storm surge affect the coastal area of the remote island. Usually the wave breaks on the coral reef, but the sea water right up on the top to propagate towards the coast, and it will cause the land flooding. Coastal water depths and topographic information are very important for this projection, but they are very hard to maintain the information. For these purposes, we carry out our technology to identify the land topography using various kinds of satellite. We developed our technology to together with NTT data to up to 50 centimeter spatial resolution of a terrain model using commercial image, satellite image. So this is the difference between traditional satellite image derived terrain model and our cutting edge technology, multi-view stereo technology. So the very precise land topography are expressed with our technology. So we found that these technologies are useful in the to understand the circumstance in remote island. So this is something one of the typical example of the Tokyo metropolitan area. Sorry, the movie is a bit slow and it cannot be played, but this is the 3D view of the Tokyo metropolitan area. This is only taken by image, satellite image, no drones, no air. The purpose to this project, we have evaluation between the ground survey and our result comes derived from the satellite image. So the RMC error is within the 1 meter or 50 centimeter with that conditions. So we have we sure to use the data of these terrain models. So this is the Fiji capital region topography. The brownish area is a landside, and these gradations are expressing the topography of the landside derived from our technology. So with a 5 meter spatial resolution. For the bathymetry, the topography of the seafloor is also necessary to predict the future situation of the inundation in the coastal area. So we also carry out another technology to understand the shallow water depths, the bathymetry. We call them satellite-derived bathymetry, SDB. Using an optical image of the satellite to understand the condition of the shallow water bathymetry. As you can see, together with the land topography area, continuously the coastal shallow water bathymetries are continuously modeled in this image. So we can predict, so by using these land and bathymetry information as a boundary condition of the model, we can predict the future situation in the inundation in the land remote islands. So this is the simulation of the how do we carry out to predict the situation in the inundation. This more details are presented from the Tajima Sensei on the after my presentation. So I will skip this method. So this is one of the example, the same place that I showed, the Suba area in Fiji. In the current situation, the red line shows the coastal line right now. But in the future, and the climate change happen according to the climate change scenario of RCP 8.5, and in that situation, the storm surge will increase the scale to inundate severe in the land side. But you can see the red area is covered by seawater. You can compare to the current situation and the future situation. That information is very useful for the country, small island country in Pacific areas. So this was done in the by the last year, and this year, physical year, we predict these expand the area to the 22 area chosen from the South and North Pacific regions. So I will show you the example of what we created to visualize the result of the simulation. So this is a modular city. You can select from this menu. I choose modular city, and the hazard type surge inundation, and the return period of typhoon is 100 years probability, and the scenario as the same I showed RCP 8.5. This is a situation in the modular city right now. If it goes the year 2030, you can see the inundation area and the depth. The depth is overlaid on the picture of the satellite. You can zoom up and zoom out. You can move the map here so that you can understand the situation in the widely. The color of the inundation area is according to the depth of the inundation in the color table right here. So the year 2050 and year 2100. So you can see the red area, which is the deep inundation area, is expanding in the future situation. You can change the return period here, so you can change the size of the typhoons and also the climate change scenario as well. So this is the Tsugaru Fongafare city. You can change the target area from our 22 selected area. You can change the years here. So this website will launch soon to show everyone to understand the situation in the small country in Pacific regions. So this is the very simple introduction of the viewer tool, web tool, ready to be launched. So this is the first part of my presentation, introducing the satellite technology that we use, and also the introduction of the viewer tools of to show the result of the prediction. Thank you very much. Then the next speaker, coastal modeling and selected site in SIDS by Tajima Sensei in University of Tokyo. Tajima Sensei, please take your microphone.
Okay, so hello everyone. Can you hear me?
Yes, thank you very much.
Okay, so let me share my screen. So I hope you can see my slide. So thank you, Mukaida-san, for the introduction. So my name is Yoshimitsu Tajima from the University of Tokyo, the School of Engineering, the Department of Civil Engineering, and I'm in the Coastal Engineering Laboratory. So as introduced by Mr. Mukaida, my task in this project was for estimation of coastal hazard for 22 islands. So using 10 minutes, around 10 minutes, I would like to briefly explain how we estimated coastal hazard. So as was already shown, so this was the overview of the developed system. So first, we use stochastic typhoon model for generation of the typhoon. And basically our estimation is based on Monte Carlo simulations. So we randomly generate many typhoons. Then for each typhoon, we compute coastal hazard. then we estimate the probability of each event. So again, so we use stochastic typhoon model for estimation of generation of typhoon. Then for this model can evaluate or actually generate and estimate the track and also central pressure of typhoon or cyclones. Then after the track and central pressure was given, then we use empirical typhoon model for computation of the wind field and also the pressure field. Then we apply wave model, and maybe many of you may be very familiar with SWAN or SWAN. So basically we apply SWAN for computation of the offshore wave conditions. Okay, so therefore by using these models, we can obtain offshore wave condition at each target site with based on the different typhoons. So based on those data, we can obtain probabilistic offshore wave conditions. Then, as was shown in Mukaida-san, so we have the 15-year return period and also 100-year return period. So we determine the representative wave conditions for 100 years and 50 years. Then we apply wave surge current model for estimation of actual coastal hazard. So let me briefly explain about each model. So let me start from the stochastic typhoon model. So this stochastic typhoon model is basically based on the cyclone data in the historical cyclone data. And also we apply GCM for future, the projection of the influence of change of typhoon cyclones. So basically stochastic typhoon model first determine the initial location and pressure and moving direction and velocity of typhoon. Then we just compute the change of location of typhoon and pressure of typhoon one by one by changing your time step. Then the characteristics of moving direction, velocity, and change of pressure, they're all based on the historical data, so that the average of these characteristics agrees well with the actual data. Then, because this is Monte Carlo type of simulation, we apply autocorrelations so to account for the uncertainty of the change of typhoon, so that we can generate many typhoons. And basically, average agrees with the data. However, we also account for certain uncertainty to account for the change difference of each typhoons. Then the wave model, maybe I should omit. So it's very well known, the wave model, offshore wave model SWAN. So for each typhoon, once you specify track and the track and pressure of typhoons, then we can estimate wind field. Then based on the wind field, we can compute wave fields. So this movie, they are corresponding to each different typhoons. Okay, therefore, for each computation, actually, we need to take maybe a couple of hours for computation of the wave field. But then for a certain specific target site, actually we generate 10,000 typhoons. Then in the case of South Pacific Island, in the South Pacific area, roughly speaking, we have 10 cyclones in each year. Therefore, if you generate 10,000 cyclones, that corresponds to 1,000 years type cyclones. Okay, then we cannot compute the 1,000 cases by using wave model. Therefore, so out of 10,000 typhoons, we picked up 30 or 50 representative typhoons, which gives you the largest wind field at the target site. Okay, then based on the selected typhoons, we compute wave field. Then based on this data, we can estimate wave height and period at target site, offshore of the target site. Then based on those data, we can obtain this kind of figure. So here the horizontal axis is return period and the vertical axis is significant wave height. And this is in the case of Whaleoro in Samoa. So as you can see, so then actually the dark plot is based on the actual typhoon record. Then white plot, the solid blank plot, this is based on our stochastic typhoon model. So if you just use the record, historical record, then we have limited number of data. Therefore, we cannot really estimate the event with return period of higher than say 1,000 years. Okay. However, by using stochastic typhoon model, we can generate many typhoons. Therefore, we can also estimate the event with return period of more than several hundred years. So by using this, we estimate wave height, offshore wave height conditions for return period of different years. So in this case, we selected 100 years and 50 years. Then we applied it for wave surge current model. Then, so I omit the very detail of the wave surge current model, but this is basically similar to X beach type of model. So wave field is similar to a SWAN model, so it's energy average, phase average model. Then in addition to wave field, we also accounted for the change of the water level or storm surge. So wind-induced shear stress and also wave-induced radiation stress. Then waves are actually broken at the edge of coral reef. However, broken waves generate have radiation stress that elevate your water level on the reef. So those phenomena can be accounted for in this wave surge model. So this is just an example for the case of the Pareolo. Then top figure shows how your water level change. So it corresponds to surge. Then the bottom figure just shows the significant wave height. Then black area is on the land. Then, yes. Then here is the edge of the coral reef. So as you can see, almost the red color means higher wave. Then the blue color, green color means lower wave height. Therefore, as you can see in the bottom figure, most of the waves are broken at the edge of the coral reef. However, if you look at the surge, then due to broken wave, water level is forced to be elevated. Therefore, as you can see on the reef, we observe a very high water level. So this actually induced the inundation. And at the same time, even the waves are dissipated, however, we still have certain wave component. Therefore, for this the computation of inundation, we also account for the wave overtopping due to the component of the wind waves. So this is one of the examples of computed inundated area in the case of Pareolo Airport in Samoa. Then, so those are the overview of the model. Oh, sorry. Then at the same time, we also need to account for the influence of the climate change. So for influence of climate change, we apply GCM, so future projection of different typhoons. Then based on GCM, we picked up the typhoon event. Then we compare how the typhoon or cyclone will be affected by the climate change. So this one just shows the number of typhoon hit at each locations. Then the top figure shows the present climate. Then the bottom figure shows RCP 8.5, future climate. So in terms of the number of typhoons, then we cannot see clear difference in these two. Then, so this one just shows the minimum, the lower pressure, the central pressure of typhoon. Then, so present the climate and also RCP 8.5 climate. So you can see that if you look at the minimum value, extreme minimum value, then we might have certain intensification of the cyclone. So minimum typhoon is slightly lower in the case of RCP 8.5. However, if you look at all the data, then the very significant difference was not really found between present climate and RCP 8.5 climate. Okay, and especially in terms of the mean value, which is used for our stochastic typhoon model, they are nearly same. So as you can see in the black and red, they are nearly same. However, standard deviation, so that accounts for uncertainty of a typhoon cyclone change. Then we see the slight difference between RCP 8.5 and present climate. Therefore, in this model, we slightly increase the standard deviation that is included in terms of the uncertainty of typhoon, the generation of typhoons. However, we also found that based on analysis, the intensification is typhoon is the influence of the intensification of typhoon is relatively small compared to the influence of the sea level rise. Okay, so sea level rise was more dominant in terms of the coastal hazard in those islands. So those are the overview of our model. However, so this year, actually, we need to apply this model for different islands, so 22 islands. Therefore, our model, especially for SWAN, is not good enough to extend our model for many, many countries. Therefore, in this year, we also applied some different simplified model to speeding up the offshore wave computations. So roughly speaking, so we don't really have to estimate spatial distribution of wave height, but we also only need to account for, or only need to estimate only single point. So in this case, Tsuba, Fiji. Then if you were to compute only single point, then we don't really have to compute all these areas. And instead we just draw these lines. Then we just compute wave propagation, generations, dissipations along these lines so that we can only get the wave information at this target point. So by using this model, so each typhoon case, computation cost was much lower. So now we can compute each event in several seconds. Therefore, we can apply this model for estimation of offshore wave conditions. Then this is actually a comparison between SWAN and the proposed model. Then with the return period of different years, then we can see that this black dot, this is based on the present model. Then green one is based on SWAN. So they agree reasonably with each other. Therefore, in this case, we applied this model, line model, for estimation of offshore wave. So by using this, we can estimate inundation for each island. And this figure just shows the water level in the inundated area in each island. So this is in the case of Northern Hemisphere. And also this is in the case of Southern Hemisphere. Okay, so more detailed information will be already provided to LESTEC. Then they show all the inundated area as was introduced by Mr. Mukaida. Okay, so that's all my presentation today. And I'm happy to get some question or comments. Thank you very much.
Thank you very much, Tajima Sensei. So we have, we would like to have a couple of questions from the everyone here. Are there any questions? While raising your hands, I would like to introduce one question from the chat box. There's a very Solomon interest from Solomon Island. As I introduced in the viewer tools, there is a result of the Guadalcanal city in Solomon Islands as well. So as I introduced before, you can select the surge inundation return period 50 years or 100 years. And we can choose 2.6, RCP 2.6 or 8.5. That will show you the future situation in the coastal areas. So present time, okay, but 2013, 2015, the area and the depths are increasing especially in the coastal area and around the river mouths. Yes, the maximum depth estimated is 2 meters, but area is expanding if the situation getting severe. So this is the one of the example in the Guadalcanal cities. This computation based model that explained by Tajima Sensei and the boundary condition of the satellite-derived information, DTM, and bathymetry. Okay, so this is the one of the introduction. If you have any, are there any more questions? Okay, so I will move to next step. So this is again from my side to show you the risk assessment tools and the introducing the core algorithm of the algorithm using these tools, including some videos. So I will share my slides. So risk assessment tools using a core algorithm we have developed. This is the simple, it is not the simple, but the concept of the cost and the benefit estimated by tackling with issues on the climate change. And based on the flood hazard prediction, we could understand the size of the disaster, the amount cost of the disaster if the no countermeasure was taken. So economic damage calculation is here. And the consideration of the countermeasure construction, gray, which is the ordinary infrastructures, and green, which we set green as a using coral to prevent the high wave storm surge. And the mix is using both gray and green and gray measures. So the cost of the measures can be computed as amount and the effect the countermeasures were taken, the damage calculation can be calculated by this. So the subtracting from the no countermeasures and after countermeasures, the $3 million in this case is the benefit. And the cost of the to take a measure, we need money to tackle with that issues. So we assume it's a 1 million. In that case, it's ideal. The 3 million subtracted by 1 million is a 2 million. This is a gain of the benefit. This is a pure gain that tackling countries will get. Taking more closely to the benefit that we get by after the countermeasure, non-economic loss and damage and the direct damage assessment is to prevent the disaster. So indirect and the non-economy damage is something we consider to have a better environment for the tourism and better fishery condition by using not only a gray measure, but also the green measure to prevent the coral reef environment. So this is a simple diagram of the concept that we developed. So this is the estimating the cost of the measures, gray measures and green measures. As you can see, the right hand of the graph, the construction fee will take in the first year, and the maintenance fee will be accumulated in the year by year. So the construction fee for the gray measure is to have the infrastructure in the coastal side. And the green measure, we assume that to maintain the high temperature tolerant coral transplantation and water quality maintenance as the major of the green measures. So this is the cost. The benefit is a little bit complicated. As you can see, the direct benefit, which to prevent the disaster, is seems like right upper graph. So the subtract of the damage with countermeasure and the damage without countermeasure is the benefit, and the benefit will accumulate year by year linearly. And the ecosystem service or indirect benefit is also taken into account, like in the right lower graph. That will also make a benefit year by year linearly. So considering with these two benefit of the each measure, green, gray, and mix, ideally we can see as the time series of the relationship with the time series of benefit and cost is for the gray measure is something like this. The blue shows the cost and gray shows the benefit by gray measure, and the subtraction between the cost and benefit showing in the yellow line. So this is something like we expected for the gray measure. In the green measure, for the benefit showing in the green line, that will addition of the direct benefit and the indirect benefit. So that will increase the amount of the benefit. At the same time, in the inverse point of the cost and the benefit becoming more near to the current situation, current time. So this is the mix of the measure, mix measure. The benefit is shown in the light green. It will more get the benefit by using partially gray measure to prevent more for the disaster, more than the green measure will prevent. So for this to understand this situation in more interactively, we developed another tool, but it's still a prototype, and we are now working on for the better user interface. But I would like to introduce a little bit on the web again. So, okay. So this is the one of the example. The left side, the map controller that will able to show the location and the type of the hazard and the return period of the storm and the climate change scenario, as same as I introduced in the hazard viewer. The big difference is the right-hand side graph, and the number predicting number shows in the lower left side. Also you can close up and zoom out with the GIS interface, and as you can control the time controller, you can see the amount of benefit on the graph, each mix gray and green. And the condition of the inundation is showing in the GIS part. And also you can see, compare each measures, green, mix, and gray, and no. So this amount is B by C in this year, that you can see in the very future situation, the mix measure is the best choice. And then the green and gray. To shows the to set the condition, you can change each parameters here. The cost and the benefit that you can change for the each measures. So you can explore each condition in your country or the area of interest. So that is the very simple introduction, and we are still under the development and release on the web soon. I will inform you again. So the things that I talked is very complicated, so that we made a movie to understand more easily. But the movie is still on the development, but so and the movie is only showing the summary of the result. So please understand the function of the prototyping tool is just introduced, that you can manage all the situation and the parameters by own. Okay, so the please, I will show you the.
This video is a demonstration of the use of a web application designed to provide a concise understanding of the EBPM logic generation mechanism. According to the latest IPCC findings, if global warming continues at its current rate, sea level rise could be 1 meter by the end of the century. Sea temperatures will also increase water vapor, causing tropical cyclones to intensify and coral reefs to bleach. In SIDS, most socio-economic activities are concentrated in coastal areas, and some countries, such as atoll islands, have low elevations, making them vulnerable to flooding hazards caused by external weather forces. The prototyping of the policy decision-making tool was prepared by RESTEC under the overall guidance of the Ministry of the Environment, Japan. The purpose of the tool is to provide support for policy decision-making in addressing inundation. The tool monitors regions under risks against inundation and provide hazard predictions for critical socio-economic infrastructure, mainly for 22 islands in 14 countries. The risk assessment is based on the simulations of existing stochastic models and on global warming scenarios. Adaptation measures to flood disasters in the coastal areas of island countries assumed in this prototype are classified as gray measures for breakwaters and wave-dissipating blocks and green measures for conservation and rehabilitation of reef-building corals. This is what an ideal coastal disaster prevention engineering project with gray measures would look like in the current climate. With ideal gray measures, we can prevent flooding hazards in a post-warming world and protect coastal socio-economies from damage. On the other hand, concrete structures not only damage the natural environment and landscape, but may also affect the coastal fishing and tourism industries. In addition, since future climate change involves uncertainty, it is necessary to harmonize the expected disaster prevention effects with the cost, such as the height of the structure. This is what happens when a reef-building coral conservation project is carried out using green measures that are ideal in terms of natural ecological engineering to supplement disaster prevention functions. Healthy reef-building corals are said to have an upward growth potential equal to the average rate of sea level rise. If the reef-building coral is healthy enough to withstand the rise in sea temperature, the depth of the coral cover area in the reef flat, including the reef crest, is said to be constant as the rate of coral growth and sea level rise are balanced. In other words, the wave dissipating effect of the reef ridge on offshore waves is the same as before global warming. The increase in inundation hazard will come from sea level rise and changes in tropical cyclones. The real function of coastal disaster prevention realized by the conservation and restoration of reef-building corals with high temperature tolerance is nothing but the wave dissipation function of reef ridges. Compared to conventional gray measures, the ability to protect the socio-economy from the risk of flooding hazards is limited. However, when corals are in a healthy state, they maintain their natural regulating function of keeping the depth of the shallow sea at or below a certain level for a long time. Regardless of the rise in sea level caused by global warming, it is expected that the maximum flooded area will be reduced in the future, although it will take time. Green measures generally have the potential to conserve or create new ecosystem service values. For example, the conservation of coral reefs not only protects the livelihoods of coastal fishermen and tourism industry workers, but also creates employment opportunities associated with conservation and cultivation work. In this way, the benefits that green measures can bring to island nations are very significant. In order for island countries to adapt to the effects of climate change, such as sea level rise, it is very important to maintain the land based on ecosystem conservation. This prototype aims to compare the costs and benefits of gray and green solutions to improved climate change adaptation. The cost of constructing a coastal protection facility is calculated by multiplying the facility length by the unit cost. The maintenance cost was calculated by multiplying the above cost by the expected number of years. The benefit amount is the difference between the damage area caused by coastal inundation without countermeasures compared with the ones with countermeasures. An example of a calculated graph is shown here. It is assumed that construction will be completed in 3 years, after which maintenance costs will be added annually. The social discount rate is assumed to be 10%. It can be seen that benefits gradually rise over the construction period, and at some point the benefits exceed the costs. green measures are envisioned to include the planting of high-temperature tolerant corals and water quality maintenance measures to protect the corals and to calculate the cost of such measures. The benefits of green measures includes increased tourism and fisheries revenues benefited out of the maintenance of ecosystem services. In addition to the maintenance of wave dissipation effects by corals, the amount of this increased benefit will be cumulative from year to year. An example of a calculated graph is shown here. The rise in benefits is gradual, but the cumulative amount grows. When we compare the gray and green measures, we can see that the gray measure reaches the break-even point earlier than the green measure, but produces more present value than the gray measure. Mixed measures are based on both green and gray countermeasures. Mixed measures are used only where the hazard is vulnerable and more countermeasures are assumed to be necessary. The cost-benefit calculation method is the same as for the aforementioned gray and green measures. An example of a calculated graph is shown here. Comparing mixed measures with gray and green measures, it can be understood that mixed measures generate greater benefits than gray measures, although the break-even point comes earlier than gray and green measures. We hope that this prototype will help you to determine when green adaptation measures are more reasonable than gray adaptation measures by calculating the cost of adaptation measures based on the amount of damage that future external climate change will cause to socio-economic infrastructure, and by considering the value of ecosystem services.
Okay, thank you very much. This is the end from my side, and takes a little bit longer time, and I would like to hand over to Kayane Sensei of University of Tokyo for coastal modeling of understanding coral ecosystem and green infrastructure. Kayane Sensei, floor is yours.
Hi. Good afternoon and good morning, everyone. My name is Hajime Kayane from University of Tokyo, and I'd like to review the function coral reefs as a green infrastructure and stress the need to include restoration activities of coral reefs as well as gray infrastructure, gray technology as a countermeasure project against sea level rise. Sea level has already risen 20 centimeters due to the global warming and is projected to rise 30 to as much as 1 meter at the end of this century. And coastal zone is threatened by this rising sea level. In particular, the low-flatted atoll islands shown in these photos. This is Kiribati and Tsubar, and those two photos are from Majuro atolls. All these atolls have an elevation of only 2 meters or 3 meters, so they are critically threatened by rising sea level. And the coral reefs form the foundation of the islands, and now is protect the island coastline from ocean swells. And the breaking coral chips forms the island itself. So the coral reefs are very important function for island sustainability. All these islands or coral reefs, the seaward edge of coral reefs, shown covered by the white waves are formed by reef crest. Reef crest at the seaward edge breaks ocean swells. And this is the reef crest is formed by a corimbos type or thick branches of corals, mainly Acropora species. Upward growth rate of the reef crest as a landform, not corals biological, but geological upward growth rate of coral reefs at a reef crest is estimated by as 20 to 50 centimeter over 100 years, revealed by geologic studies. So the rising sea level in this century is estimated to be another 70 to 101 meters. So the reef crest has a potential to keep up with the rising sea level as far as corals are healthy. As far as these corals, which form the reef crest, is healthy. However, corals are degraded by local stresses such as eutrophication, sewage, and the healthy corals shifted to the algal bloom, and also global stresses such as bleaching or ocean acidification. If 1 meter of reef is lost, or 1 meter of sea level rise without growing the reef crest or coral reefs, flooding may increase by 23% and impact 62% more people and 90% more property, and increase a large amount of damages. These estimates are for the US remote islands. We need to restore coral reefs by improvement of coastal environment first, and then we need to restore coral reefs by artificially. We have developed several technologies of coral restoration. This is one example. The Ministry of Land, Infrastructure, Transport and Tourism has installed coral transplant racks, which will be applied as submerged reef structure to break ocean swells. A fisheries agency in Japan established coral mass culture technology, by which we succeeded in breeding juvenile corals from eggs and sperms, and then outplant them to a frame on the reef, like this. They can be applied as submerged reef structure to break ocean swells against sea level rise. Monetary value of ecosystem services of coral reefs is the highest among all the biomes on the earth, including not only land, but also not only ocean, but also land. The coral reefs have the highest value of economic values, as much as large as $350,000 over 1 hectare for a year, over a year. The largest portion of the service corresponds to the function of natural breakwater. But coral reefs provide many other services such as food, raw materials, genetic resources, or disturbance moderation, aesthetic information, and recreation. This service estimates rather put low value for food or fisheries, which must be larger in the small island countries. On the other hand, at present, restoration cost of coral reefs is averaged to $400,000 over 1 hectare, almost the same value as the ecosystem service of coral reefs. But you should be note that the ecosystem services is estimated as over 1 year. Every year, this service will be provided by the coral reefs to the humans. But this cost is without over a year. So this cost is can be, we need this cost at once. We need to pay another cost for to sustain or maintain the restoration of coral reefs, but the services continue eternally. We can receive the service every year by coral reef as far as the reefs are healthy. Moreover, the restored coral reefs will grow autonomously to keep up with the rising sea level, to keep its function of natural breakwater. So I'd like to stress again that we need to include green infrastructure in the project against sea level rise. Thank you very much.
Thank you very much, Kayane Sensei. I'd like to take one short question if you have from the audience. Do there any question to Kayane Sensei, me, or even with Tajima Sensei is okay? Any question or comments? Okay, we have a time of discussion in the last part, so I would like to move to the next presentation from Nonaka-san of the Nikkei Sekkei Civil Engineering. The title is Case Formation of Applying Green Infrastructure Technologies.
Thank you very much.
Yes.
I'd like to share my screen. Just a moment, please. Moment. And can you see my screen clearly?
Yes, we can.
Okay. Just a moment. Thank you, and just a moment. Thank you for attending this meeting. And I am Nonaka and of Nikkei Sekkei Civil Engineering. I'm going to make a presentation, and as one of the study team of the idea of coastal disaster prevention. Just a moment. Program with the ecosystem-based adaptation. And this study has been introduced by the Ministry of Environment Japan, and in this fiscal year, and this March is in the last month of our small project. So yes, I'd like to make a presentation and with the information which previous speakers already mentioned, and about the calculation of the future and higher waves or coral reef restoration. And we are making the future program to restore the coastal area from the climate change impact. Today's message is designated in the two parts. The one part is a proposal of one idea for the coastal disaster prevention program and climate change adaptation. Just a moment. My screen is a bit different. And then, we have to show, and we have to say in this presentation is the beginning of a talk about future cooperation. This is the two main topics of my presentation. And as the previous speakers mentioned, the coastal and coral reef is very important and role have a very important role about the dissipation of the water power, and also the coral reef can grow up in a lot of ecosystem and living things, and also good for the fisheries, and also debris from the coral reef and can make the coastal and coastal zone beaches. And as in the movie and mentioned, and in the right figure, we can see if the coral reef and cannot grow and healthily, and higher waves and will get into the coastal area from the outside ocean, and that is also affected by the sea level rise in the future. So this is a very important, crucial matter we are focusing on today. And we are currently studying about these kind of sites to make a concept of our program. This is in the figure and the pictures of our image of the possible sites. The left column is kind of the very vulnerable area from the higher waves, and the central and the pictures and showing the very inundation prone area from the high waves or high tides. And in the white column and shows the vulnerable and the coral reef or already breached in the coral reefs. Those kind of parts are where we are focusing on. And as you know, and very well, this is the change in the sea surface temperature and the former and previous 100 years from 1891 to 2012. The reddish part is in the increased temperature in the ocean of the world. So the almost part and the water and temperature of the sea the reason has risen very much. And the picture in the right side is the vulnerability and the impact and risks to the ocean ecosystem from the climate change. I'm sorry, my screen was very small. And as you know, and this came from the SROCC and IPCC report and published in 2019. The right figure and describes the warm water corals is the most vulnerable and for the impact and risks to the ocean ecosystem from the climate change. This figure is difficult to understand, but in the purple color is shows and the high risks and the high impact caused by climate change. And in the left side, and the most left side column is warm water corals. So this part has the much in the purple zone, and in comparison with others. And the next one from the right and the left side one is kelp And the next is the seagrasses. And gradually in these, each ecosystem and the risk of the impact of the ecosystem and gradually decreased from the left to the right. So in this and particular types of the coastal and the environment, the warm water corals are the most vulnerable for the climate change, and was reported by IPCC. So that we are focusing on the vulnerability of the coral reef in the future. And next page is coral bleaching and cause and inundation and coastal erosion and the damage on the fishery and damage on the tourism industries. So those impacts are already mentioned by the former speakers, and those kind of damages and also bring risk in lives and economic losses, as we mentioned previously. That's a very important word in the Pacific Island countries. And so, we made the basic policy of the program. This is the tentative one, and this is the first time to express for the euros today. And the first one, country and the targets, and we are focusing on the 14 countries in the Pacific region and coastal zones and of those countries. The 14 countries are described in the later part. And number two is purpose. A is in Pacific Island nations reduces the damage caused by the higher storm and storm surges due to climate change, and realize sustainable communities in coastal area. And B, and by restoring coastal ecosystem of coral and mangroves and local culture and fishery and tourism and other sustainable, make and local culture, fishery, tourism and other sustainable. And in order to keep to function and the function of the coral reef sound, restore the coral reef where bleaching is obvious. Just a moment. My screen is covered by this meeting system. Thank you. And second, take measures to reproduce coral species, and that can be resistant to the effect of climate change and to deal with domestic wastewater and inflowing sediment. And number three, in addition, engineering measures such as a seawall or revetment may be introduced if necessary. This is in the basic structure of our the basic policy. And next, this page is the designate the basic policy into the very simple figures. The upper figure indicates no response cases. As the previous speakers already talked, and the sea level rise and stronger storms and coral bleaching also affected the coastal area and for the people. And but against those future risks and current risks, and we want to make a actual program for those kind of vulnerable areas with in the ecosystem-based adaptation. EBA is namely in the restoring the coral reef and the mangrove forest. And right side is the engineering and countermeasures. those and should be mixed with the economical point of view, and good for the good and environment for the coastal zone. So comprehensively, and we have to make a good and program depend on the each condition of the each site. That is in our ideas. And this page is a little bit and breakdown from the basic policy of our program. And the first one is the feasibility study and the planning for each site. We don't know detailed information or condition of the 14 countries. So we should study into topography or ecosystem of society or etc. And formulation of adaptation plans and based on ecological and engineering measures. That is the first steps. And the second, the restoration and conservation of coral. And that is in the restoration and conservation of coral by the sexual reproduction. And cutting off the branches of coral and surviving coral can sometimes can be cut off the branches from the surviving coral and removed and replaced to the other devastated area or breached area. And those kind of method is making clones for the other area. Clones means perfect twins from the one coral. And it is, for example, this has in the future, and all the coral may have the same face and the same hand or same knowledge or same ability or all same and in the twin, the clones from the one and coral. So those kind of method is very vulnerable for the future against the change of the condition. So in Japan, and the sexual reproduction method for coral resurrection has been developed for many years. So this is the one topic of the coral resurrection from Japan. And the second is in the wastewater treatment. If the coral reef affected by the wastewater from the human activities, so we have to cope with those problems. And also, if the coral reef is affected from the small particles from the inland, in those cases, we should have countermeasures against turbid waters from the land. So we should have a study in the comprehensive countermeasures against to restore and conserve the coral reef. That is the second part. And third part is the restoration and the conservation of the mangrove forest. That is, yes, and could be explained as the same as number 2. And number 4, and other countermeasures, as I mentioned, and the embankment and replacement on the beach nourishment or other countermeasures should be taken if necessary. Or the relocation of strengthening of housing and the facilities is also considered if necessary. These kind of comprehensive ideas should be studied depend on the condition of each site. And this is the little bit detailed information. Skip. And this is a tentative image. This is not strict. This is the kind of image. If the pink the zone is affected by the higher waves or high tide in this stronger cyclone, then we should, and if the coral reefs are already breached or damaged by some reasons, we should make a plan to restore the coral reef. against the bleaching or devastating. And the red line is the example of the future zone should be restored. And if the land is more vulnerable and with the natural and best adaptation, then we have to make a plan to construct and embankment or revetment at the shoreline like this. This is the kind of some image. And also, if in the wastewater is affecting the coral reef bleaching, we should have another plan to cover the wastewater from in the cities or towns directly into the ocean. And we should cut off those wastewater, and we should treat those wastewater and purify before run out and release the water into the sea. These kind of comprehensive ideas should be taken. And the last page is the second topic, as I mentioned at the beginning, and the cooperation structure and the ideal roadmap, and of which MOEJ is aiming. The MOEJ is the abbreviation for Ministry of Environment and the Government of Japan. This is the project owner of this idea. And the ministry are focusing on the 14 countries, which you are attending this meeting. And on the right side, these countries are also joined spread. And the lower tables describes the abstract and roadmap from the 2022. The highest row is meaning in the MOEJs and activity, and central middle part is an international organization accredited entities for GCF or other international donors. And the lower part is the Pacific Island countries. So for you are participating now. And so the first year, and from the next month, next month, April is the beginning of the Japanese fiscal year. So MOEJ is planning to start number one, coral reproduction experiment in Palau. And number two, making guidelines relating to the program, this program. And number three, need hearing and discussion and site selection of these program ideas. And number four, study a concept note for the GCF. And these activities cannot be run by only in the MOEJ. So the MOEJ have to cooperate with the possible accredited entities or other donors, even in the first years. And in the first years, JICA currently creating and running cooperative project on the coastal environment in the Palau. Yes, that is already started. And we would like to explain about the third part and the Pacific Island, for the Pacific Island countries, the needs hearing of the program idea, which today I mentioned, I explained, and discussion about these matters. And this MOEJ needs and site selection with your countries. And also, MOEJ should make the meeting or discussion to study a concept note, to prepare a concept note for GCA. So and the MUJ and should take and those and the cooperative and activity with the EU countries and the yes possible and accredited entities for this year. And 2023 and 2024, if and the concept note and words and clearly and prepared, depending on the actual site and the actual programs, then and all the team should start further research and feasibility study and detailed planning and preparation for funding proposal. So after 1 year or 2 years, and finally, and we are thinking about funding request for the Green Climate Fund this year, or international cooperation agencies to realize those ideas into the practical and activities. This is in the beginning of our first explanation announcement of our ideas of the program. Thank you very much. And if you have any question or any requirement, we would like to hear those opinion from all of the participants. Thank you very much.
Thank you very much, Nonaka-san. Okay, so this is all our presentation from our side, and would like to have a question from the audience. And already several questions showed in chat box. I would like to introduce a little bit. Okay, the first one is the thank you very much for interesting presentation. Have you trailed out these initiatives in any of the Pacific Islands? From Vanuatu, Lena William. Yes, the providing these kind of information that we introduced is our first challenge, and we are glad to provide the information via website and to the countries. But the transplanting of the corals, the techniques already developed, and we also would like to enhance into the small island countries. If there's any opinion or follow-up from Kayane Sensei of Tokyo University, could you please comment on this, please?
Hi, thank you very much for your question. Coral restoration technologies have been developed in several sectors in Japan, and we are willing to apply these technologies to the coastal protection project plan against sea level rise in island countries. However, this technology, coral restoration technologies, must be implemented with improvement of coastal environment, as the corals never grow up under the bad under polluted environment. So we need to mix the coastal ecosystem environment improvement project with coral restoration projects. And also this coral restoration technology should be implemented with a best mix of gray and green technologies. But gray and green technologies never conflict with each other. The viewer respect showed the first step for the implementation of green and gray technology, I hope. Thank you very much.
Okay, thank you very much, Kayane Sensei. Okay, and the next question is from Environment and Conservation Division of Kiribati. Are there any other factors that could be considered in the model, like development, distribution, etc.? Yes, the more we if we going to more accurate prediction, we need more information. I assume like very precise land use and land cover information and sort of things. So that kind of condition of the land side, also with the ocean side, will make our prediction more precise. So more information is welcome, and we are willing to take into our model. And another question from the same side, to what extent will the model applicable to small line atolls like Kiribati when we don't have cyclones? Yes, that is a very good question. So we are, I think I would like to have some answer or comment from Tajima Sensei of the University of Tokyo, but my understanding is that this model is basically driven by ocean surface height rise and the empirical typhoon model. So is my understanding right, Tajima Sensei?
Yes, you are right. So I forgot to mention, but so far our model is limited only for the coastal hazard induced by cyclones or typhoons. And that is actually one of the reasons why I introduced different wave model. So in this different wave model, we could account for wave propagation from the very far field. Therefore, in near future, the next actually task for me is to include such kind of the wave propagation from the far field, the swell from the south, north. So then I think it can be applicable for estimation of coastal hazard. So now only the problem is for estimation of the offshore wave conditions. Then once offshore wave condition is determined, then we can apply the same model for computation of the inundation around the coral reef island. Thank you very much.
Thank you very much, Tajima Sensei. From the remote sensing point of view, land deformation is one of the factors that we need to take into account. If the land inundation, land sinking happens in the coastal side, that will also affect the inundation of the seawater. So that is the answer from our side. And yes, from Alatawa-san, how much time does it take for that 4-stage framework to be completed or achieved? So you mean the 4-stage framework is the very last part of Nonaka-san's presentation. Do you can you answer to this question, Nonaka-san, please?
Thank you for asking. Maybe in some parts of question and was described in the last pages of my picture, and yes, and it will take some years to complete or achievement the project, or before and make and funding and mobilize the funding. Before mobilize the funding, it takes 2 years or 3 years. This is a little bit we have to make an effort, and this is the starting point and first year, and we should, and as I mentioned, and we should make and select and the most vulnerable and the most and the willing part of the countries for the future and planning. So the first year, this step, and the next year, next fiscal year, and we should make a more practical and feasibility study on each site. That is the basic idea of the steps to mobilize the funding and to complete and achieve the project. Is that right? Okay.
Thank you very much, Nonaka-san.
Thank you.
Okay, the next question going to be our last question because we are run out of time. From Infrastructure Cook Island, Paul Mawate-san. Kia orana o, does the model capture king tide events which have become more frequent every year for the Cook Island, especially the northern lowing atolls? Thank you very much for the question. As Tajima Sensei mentioned, that our model right now is only taking account of the sea level rise and the empirical tropical cyclone models. So, and this result of our simulation and the viewer is showing to understand and share the general information, what we are going to have in the near future. So to tackle with that issue for each island, we need to more precise information to what we are going, what we have to do. So that local information like this is very important to understand the localized adaptation, how to adapt the local issues. So these informations are very important for us also, and we need to consider all these things for next step to adapt for the local countries. Thank you very much. So if there's no question, I would like to wrap up our seminar with closing remarks. I would like to introduce Mr. Tsukada, Director of Climate Change Adaptation Office, Ministry of Environment, Japan. Mr. Tsukada, would you please make closing remarks?
Okay, thank you very much. Can you hear me?
Yes, I can.
Okay, so let me start my closing remarks. Distinguished speakers, guests, and participants, good morning, good afternoon, and good evening, wherever you are. I am Genjo Tsukada, Director of Climate Change Adaptation Office from the Ministry of the Environment, Japan, and warm greetings from Tokyo. Let me express my deepest appreciation to all participants from a wide area of the Pacific region to attend this seminar. As you already know, the impact of climate change are an evident threat to coastal areas and islands, and the Asia-Pacific region is at the forefront of tackling the climate crisis. Building resilience to climate change impacts such as sea level rise and coastal disasters is imperative for sustainable development in the region. The UNFCCC COP26 held in Glasgow, UK last year reaffirmed how important it is for us not only to reduce GHG emissions, but also adapt appropriately to climate change, thereby achieving a common goal vision to reduce vulnerability and strengthen resilience as set forth in the Paris Agreement. In addition, the latest IPCC report released last month showed that human-induced climate change, including more frequent and intense extreme events, has caused widespread adverse impacts and related losses and damages to nature and people beyond natural climate variability. Anyway, this project is a part of the promotion of international cooperation under the Climate Change Adaptation Act of Japan. As you have seen today at the seminar, we are focusing on the increased risk of high wave hazards in island countries. In addition, we are also interested in the value of coral reefs. Coral reefs are important for wave protection and also provide ecosystem services for tourism and fisheries. Our final goal is to develop a tool that displays the cost and benefits of high wave measures including coral reef conservation, thereby facilitating your access to climate funding. In order to achieve this goal, we believe it is important to continue discussions with all of you who have participated in today and with stakeholders in the island countries. Finally, I'd like to mention about Japan's continued efforts to actively engage in international cooperation in the field of adaptation. In 2019, Ministry of the Environment Japan, together with the National Institute for Environmental Studies, the Institute for Global Environmental Strategies, and relevant organizations in the Asia-Pacific region, launched the Asia-Pacific Climate Change Adaptation Information Platform, or APPLAT. APPLAT aims to enable environment for climate risk-informed decision-making and practical adaptation actions through synchronizing and harnessing best available efforts among partner countries and organizations. We began our activities for APPLAT based on 3 pillars: development and sharing of scientific knowledge, development and sharing of adaptation tools, and capacity building. I strongly believe that the output of this project will well contribute to the accumulation of tools and scientific knowledge, especially in the Pacific region of APPLAT. In closing, I'd like to thank you again for your participation in this seminar and expect your continued cooperation and support in the future. Thank you very much.
Okay. Thank you very much, Mr. Tsukada. At the very end of this seminar, I would like to have a photo session, virtual photo session. Maybe you are very get used to it. So please, your camera on to show the face if you are if you're okay. I would like to take some screenshot. Okay. If you're not willing to, you don't have to on your camera, but we are very pleased to show your face. Oh, sorry for the broken cameras. Okay. Thank you. Please say hi. Thank you. Okay. And one more shot. Okay. Thank you very much. So it was very fruitful. So this is only our beginning. So please keep in touch and we will inform you about the materials that we present today and also the URLs that we are going to launch the website. So thank you very much. And I appreciate for giving us your time very much.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Thank you. Bye.
Thank you. Thank you. Bye.
Thank you. Bye. On the Cook Islands.
Bye.
Thank you.
Bye from Kiribati.